Today, we'll explore logarithmic equations. A logarithmic equation is simply an equation that includes a logarithm with a variable inside its argument. Our goal is typically to solve for this variable. The basic form of a logarithmic equation often looks like this: log base b of x equals c. Here, b is the base of the logarithm, x is the argument which contains the variable we need to find, and c is a constant. Let's look at how to solve these. First, consider an equation with a single logarithm. For example, log base 3 of x equals 4. To solve this, we rewrite the equation in its exponential form. Remember, log base b of x equals c is equivalent to b to the power of c equals x. So, our equation becomes x equals 3 to the power of 4. Calculating 3 to the 4th power gives us 81. So, x equals 81. Second, what if we have logarithms on both sides with the same base? For instance, log base 2 of x equals log base 2 of 7. If the logarithms are equal and their bases are the same, then their arguments must also be equal. Therefore, x must be equal to 7. Third, we often need to use logarithmic laws if the equation has multiple logarithms. Consider log base 5 of x plus log base 5 of x minus 4 equals 1. We can use the product rule for logarithms, which states that the sum of logs is the log of the product. This combines the left side into log base 5 of x times x minus 4 equals 1. Now, we rewrite this in exponential form: x times x minus 4 equals 5 to the power of 1. Expanding this gives x squared minus 4x equals 5. Rearranging it into a standard quadratic equation form gives x squared minus 4x minus 5 equals 0. We can factor this quadratic as x minus 5 times x plus 1 equals 0. This gives two potential solutions: x equals 5 or x equals negative 1. However, we must check for extraneous solutions. The argument of a logarithm must always be positive. Let's check x equals 5. Log base 5 of 5 is defined, and log base 5 of 5 minus 4, which is log base 5 of 1, is also defined. So, x equals 5 is a valid solution. Now, let's check x equals negative 1. Log base 5 of negative 1 is not defined because we cannot take the logarithm of a negative number. Therefore, x equals negative 1 is an extraneous solution, and the only valid answer is x equals 5. Fourth, let's look at equations involving constants multiplying the logarithm. For example, 2 times log base 10 of x equals 6. We can use the power rule for logarithms, which says that c times log base b of a equals log base b of a to the power of c. So, our equation becomes log base 10 of x squared equals 6. Now, convert to exponential form: x squared equals 10 to the power of 6. 10 to the 6th power is 1 million. So, x squared equals 1 million. Taking the square root gives x equals plus or minus 1,000. Again, we must check validity. Since the original equation has log base 10 of x, the argument x must be positive. Therefore, only the positive value is valid. X equals 1,000. To summarize, here are the key steps for solving logarithmic equations. 1. Combine logarithms into a single log on one or both sides using log rules if necessary. 2. Rewrite the equation in exponential form. 3. Solve the resulting equation for the variable. 4. Always check your solutions to ensure they don't result in taking the logarithm of a non-positive number, 0 or negative. These are called extraneous solutions. And that's how you approach solving logarithmic equations. Remember to apply the rules carefully and always check your answers. In this video, we'll solve a logarithm problem. We are given the equation: logarithm base a of p plus 1 over logarithm base p of a minus logarithm base of p plus 2 plus logarithm base of 5 equals logarithm base a of 12. Our goal is to find the value of p. First, let's focus on the term 1 over logarithm base p of a. We can use the change of base formula for logarithms, which states that logarithm base b of x is equal to 1 over logarithm base x of b. Applying this rule to our term 1 over logarithm base p of a becomes logarithm base a of p. Now, let's substitute this back into our original equation. The equation becomes logarithm base of p plus 1 plus logarithm base of p minus logarithm base of p plus 2 plus logarithm base of 5 equals logarithm base of 12. Next, we'll use the logarithm rules to combine the terms on the left side. Remember the product rule. Logarithm of x plus logarithm of y equals logarithm of x times y. And the quotient rule, logarithm of x minus logarithm of y equals logarithm of x divided by y. First, combine the terms added together. Logarithm base of p plus 1 plus log base of p plus log base of 5 gives logarithm base of the product 5 times p plus 1. Then, apply the quotient rule with the term logarithm base of p plus 2. This simplifies the left side to logarithm base of the fraction 5p times p plus 1 divided by p plus 2. Since the logarithms on both sides have the same base a, we can equate their arguments. This gives us the algebraic equation. 5p times p plus 1 divided by p plus 2 equals 12. Now, we need to solve this equation for p. First, multiply both sides by p plus 2. This gives 5p times p plus 1 equals 12 times p plus 2. Expand both sides. 5p squared plus 5p equals 12p plus 24. Rearrange the terms to form a quadratic equation. 5p squared minus 7p minus 24 equals 0. We can solve this quadratic equation using the quadratic formula, p equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Here, a is 5, b is negative 7, and c is negative 24. Substituting these values gives p equals 7 plus or minus the square root of 49 plus 480, all divided by 10. This simplifies to 7 plus or minus the square root of 529 divided by 10. The square root of 529 is 23. So we have two possible solutions for p. P equals 7 plus 23 divided by 10, which is 30 divided by 10, or 3, and p equals 7 minus 23 divided by 10, which is negative 16 divided by 10, or negative 1.6. Finally, we must check if these solutions are valid. Remember that the arguments of logarithms must be positive. Also, the base of a logarithm must be positive and not equal to 1. In our original equation, we have terms like log base of p plus 1, log base of p plus 2, log base of p, and log base p of a. Let's check p equals 3. The arguments are p plus 1 equals 4, p plus 2 equals 5, and p equals 3. All are positive. Also, the base p equals 3 is positive and not 1. So, p equals 3 is a valid solution. Now, let's check p equals negative 1.6. The argument p plus 1 becomes negative 1.6 plus 1, which is negative 0.6. Since the argument of a logarithm cannot be negative, p equals negative 1.6 is not a valid solution. We also see that p itself is negative, which is not allowed as a base for log base p of a. Therefore, the only valid solution to the equation is p equals 3.